So here again, I have the motion diagram for a tossed ball, and the position of the ball at specific moments in time, equally spaced moments in time, are noted. And now I want to represent the displacement of the ball between each two moments in time. The way I'm going to do this is by using arrows. Displacements are going to be represented by arrows. So for example, I'm going to draw a green arrow between the first dot and the second dot, and that's going to represent the displacement of the ball over that time interval. So there it is. I've drawn a green arrow between the first dot and the second dot, representing the displacement over that interval of time. I can do the same thing with the second dot and the third dot. Now I have the second displacement, third dot and the fourth dot. Now I have the third displacement, fourth dot and the fifth dot, another displacement, and finally the fifth dot and the sixth dot is going to give me my fifth displacement. Now perhaps I should label all of these, have some notation for them, and indeed I will do so, at least momentarily. I have delta R0 to label the first arrow, delta R1 to label the second arrow, delta R2, delta R3, and delta R4 for the remaining arrows. Now, I want to think of these arrows not so much as displacements, but as average velocities. But in order to do that, I need to talk to you a little bit more about vectors. These displacements are vectors, and I have to make a connection between the concept of displacement as a vector and the concept of average velocity as a vector. I have to make a connection there. So in order to do that, we need to talk just a little bit about vectors. So let's have an aside about vectors. So vectors are going to have two properties. Vectors are going to have a property of magnitude and direction. That's why drawing arrows is a nice way to visualize them, at least at the level of an introductory physics class. So here I have a vector A, and this vector has, the arrow has a length, and it is pointing in a certain direction, so it has magnitude and direction. So for example, let's say that in some unit system, this vector A is 5 long. So here this vector has a magnitude of 5, and it's pointing, let's say, at 45 degrees from horizontal. So here I have a horizontal line segment, and you can see that vector A is 45 degrees counterclockwise from this line segment. So I've specified the magnitude and direction of this vector A. Now the thing I want to get to here is that there are certain things we can do to vectors in terms of operations and certain things we can't. But one thing we can do to a vector is multiply it by an ordinary number. We can multiply a vector by a number, or equivalently, we could divide a vector by a number. So for this vector, for example, I could multiply the vector A by the number 1/2. Or, equivalently, I could think of that as dividing vector A by 2. And so A divided by 2 would give a vector that's half the length of the existing vector. So if A has a length of 5, if I take the vector A divided by 2, then A just becomes 2.5, 5 divided by 2. Notice the direction of the vector doesn't change, just the length changes when I divided A by a number. So I need this idea, I need this operation that I can do to vectors to connect these displacements to average velocities. And I'll explain to you why that is. We are going to define the average velocity as the displacement, the vector displacement, divided by the time interval over which that displacement occurred. And so the vector displacement is a vector, and the time interval is just a number. So it's doing exactly the operation I was just talking about. So you can see that delta t scales the magnitude of the displacements, but it won't change the directions. And so all the vectors in a motion diagram that are representing displacements can equivalently, just as easily, represent average velocities. And so that's what I want to do with our motion diagram. I'd like to take the motion diagram that we've developed with our delta R0 through delta R4, and instead of thinking of these as displacements, I can think of these as just scaled versions of average velocities. So instead of delta r naught, I have v naught. Instead of delta r1, I have v1, etc. So now I think of these green arrows as average velocities, and I'm really doing well. We have the blue dots representing position. We have the green arrows, which represented displacements, and now we're representing average velocities. And so I only really have one kinematic concept to go in these motion diagrams. But before I do that, just to simplify the labeling of these things, often when we do the motion diagrams, we don't really need to label every little green arrow. So sometimes we'll just put a V down to represent that we have all the velocities denoted. So there's our V, and that's representing all these velocities in the motion diagram. Okay, we've arrived at the moment where we introduce our last kinematic concept via motion diagrams. We have an idea of what positions are, we have an idea of what displacements are, we have an idea of what average velocities are, and now we want to define the average acceleration. So to get an average acceleration, typically what we do is we look at some final velocity and we look at some initial velocity. We take the difference between the two and we divide by the time interval between the two. And so this is going to give us our average velocity. However, we haven't discussed how to subtract one vector from another. In this case, we want to subtract the initial velocity from the final velocity. And so since I haven't told you how to do that, we can't apply this definition to our motion diagram yet. So we have to make another aside. We need to talk about vectors just a little bit more, talk about how to subtract one vector from another. To do that, we should talk about how to add one vector to another. So we're going to add vectors. Let's consider two vectors, A and B. So we have these two vectors, A and B. A is this blue vector, B is this green vector. And before we learn how to subtract them, let's figure out how to add them. So it's very easy in a graphical way to add two vectors that are being represented by arrows like this. You simply take B, you take the tail of B. It doesn't really matter where the absolute positions in space of these vectors are. You're free to slide them around. They have a fixed length and a fixed direction, but they can be moved around anywhere we like. And so in order to figure out what the sum of A and B is, we're going to take vector B, we're going to slide it so that the tail of B is at the tip of A, and then we're going to draw a vector that goes from the tail of A to the tip of B. And there you have it. This vector C, which starts at the tail of A and goes to the tip of B, it represents the sum of A and B. And now that we have this process, it's pretty easy to see how we're going to do subtraction. Now we want to think about not A plus B, but A minus B. But really that's very simple, because we can think of A minus B as being a sum. We can think of A minus B just being the sum of A plus the negative of B. And again, the negative of a vector, it's very easy. We just reverse the arrow's direction. So let's do that. We have A and B here, and we want to subtract them. So the first thing we find is negative B. So we flip B around. And so now we have negative B, and now we simply add A and negative B to obtain A minus B. So we take A, negative B, we take the tail of negative B, we place it at the tip of A, and then we draw a vector that starts at the tail of A and goes to the tip of negative B, and that represents the difference of vectors A and B. And so now we know how to subtract two vectors. Now we can go back to our motion diagram and figure out how to estimate the average accelerations in our diagram. So the changes in velocity are proportional to the accelerations. We have A average is V final minus V initial over delta t. And so really all we want to do is we want to subtract each let's say we can't find the acceleration at our first position because we don't have an initial velocity pointing towards this first dot. But if we look at our second dot, our second position, we can talk about the velocity after we were at that position, and we can talk about the velocity before we were at that position, and we can subtract the initial velocity from the final velocity and get an estimate for the direction and scale of our acceleration. So let's do that. So we're going to take the velocity right after this second position. We're going to consider that. So this is our v final now, this first arrow. And then we're going to take the negative of the arrow coming into that second dot. So we want to take the negative of the arrow that points towards that position. And this is the negative. And so we want to add the v final plus negative v initial, which is equivalent to v final minus v initial. And that's going to be represented by this arrow that starts at the tail of v final and ends at the tip of negative v initial. Great. So now we have the average acceleration at the moment in time when the ball is at this second point. And so we're going to move this red arrow to that second point. And so we have an estimate for the average acceleration at that moment. Now let's do the next moment in time. We'll take the final velocity, subtract the initial velocity, and get another estimate for the acceleration. So here we're doing it. We're taking the final velocity, and we are going to add to that final velocity the negative of the initial velocity. So here I've taken the initial velocity and reversed its direction. So now again we have v final minus v initial, or plus negative v initial. And now again, a vector that goes from the tail of v final to the tip of minus v initial is going to represent our acceleration. And we're going to shift that vector over to the position where we expect the acceleration to be as shown. Now notice the acceleration in the first case is the same length, same direction as the acceleration in the second. That seems consistent, well, it is consistent with what you're going to learn about the accelerations of objects that you just throw into the air that are free to fly through the air. They will have a constant acceleration acting on them throughout their journey. We'll learn more and more about that as the semester goes on. Anyway, you can see it already that the acceleration at this second position of the ball is the same as the acceleration at that third position. And now we want to do v final minus v initial to get the acceleration at the next moment. I'm hoping you can guess that if I take the v final, the velocity just after I'm at that third point, and I subtract v initial, I add negative of v initial to that, and I draw my acceleration as a result of that, that it again is the same as the other two, because an object that you throw through the air has, roughly speaking, a constant acceleration on it. Okay, and just one last one. We can find one last acceleration. We have the 1, 2, 3, let's see, 1, 2, 3, fourth point. So we're going to do the final velocity here. We're going to take the negative of the initial velocity. Now we are going to subtract the initial velocity from the final velocity, or equivalently add the negative of the initial velocity to the final velocity. And again, we get an arrow that looks exactly the same. We have the same acceleration as we had before. We place that arrow next to the point that at which we figured out what the average acceleration is going to be. And so now we have a diagram that has positions, velocities, and accelerations on it. That's what's so lovely about these motion diagrams. You can represent all the kinematic quantities in a motion diagram. So essentially, these changes in velocity are accelerations, and we've arrived at being able to include accelerations on our motion diagrams. And so let's review. I've said it 5 times, but let's say one more time. Let's put it in writing what kinematic concepts we've explored through these motion diagrams. So we know how to represent position on a motion diagram, we know how to represent displacement, we know how to represent average velocity, and we know how to represent average acceleration. And so it's because this is such a nice way of being able to visualize all these kinematic quantities, that's why we use motion diagrams at the beginning of general physics, to help you learn about these concepts.